I will be talking, as Evan mentioned, about variational data assimilation for the shallow water equations for predicting bathymetry of the seafloor from surface waves. So what is the main motivation of this work? Well, the main application that we wanted to extend this to is tsunami modeling. And so for tsunamis, our interest is in accurately gauging their arrival time, velocity, and height at coastlines. But often they can be quite difficult to predict in the deep ocean, because in the deep ocean, their height is very, very small compared to their wavelength, which can be a couple of 100 kilometers, but the actual height in the deep ocean can only be 1 or 2 meters. What we do know is that using the shallow water equations, we can, given complete boundary and initial condition data, accurately predict the evolution of a tsunami wave. However, what that means is we require information which we often don't have complete access to, such as complete initial condition data. And often the boundary data, such as the bathymetry that we have in terms of the current available databases, is not at a resolution high enough to accurately capture the evolution of waves like this. So what we want to do is try and extrapolate the bathymetry, reconstruct the bathymetry accurately using a sparse set of observations of the sea surface height. And so we use the shallow water equations, which in this case, we look at the 1D model, which we derive from the 2D Euler equations, where the vertical dimension is averaged because of the long wavelength assumption compared to the average depth, allowing us to have a system in terms of the perturbation of the free surface eta and the velocity u. And so the total depth of our fluid is our average depth 8h plus eta minus our bathymetry, which is beta. So beta can be a function of time if you look at things like seismic shifts. However, in this case, we will consider beta simply as a function of x. And so what our goal is to use variational data assimilation to recover the bathymetry using observations of the sea surface, eta, such that the tsunami propagation can be modeled accurately. And what that means is we want to optimize, we want to minimize the error between the observations of the sea surface height, which are represented by y at some measurement points j, and our forecast of eta at these measurement points, given a guess for the bathymetry. And so the optimal bathymetry reconstruction is the one that gives us the minimum of this function here. And so the key questions we wish to address is, how accurately can the bathymetry data be reconstructed given this information and in this method? And what determines the accuracy? And secondly, if our key motivation is tsunami modeling, which is the propagation of the surface wave given to a degree of accuracy that we need it to be, then how accurate does the bathymetry need to be, our reconstruction need to be, in order to achieve the accuracy in the surface wave? And so first of all, we look at how can we find the best way to minimize our cost function j, and we do this analytically by using adjoint systems and adjoint methodology to analytically derive an expression for the gradient of j, which we can then use in a descent algorithm to set to 0. And in summary, we basically formulate a Lagrangian of j with some adjoint variables that solve a very conveniently chosen adjoint system, which allows us to come up with an expression for the gradient of j. And so the first thing we do is we use the Gateau derivative, where basically we look at the derivative of our cost function j with respect to beta, given some arbitrary perturbation of beta prime. And then taking perturbation expansions to linear order, we can rewrite it in this way here. And the reason we do this is because since this is a directional derivative, we can write this as an inner product between the gradient of j and the perturbation beta prime. And so essentially what that means is if we can formulate a Lagrangian and some adjoint variables, that lets us write this expression as something that looks like this, then that means whatever is in this position over here has to be our gradient due to the Riesz representation theorem and the equivalence of inner products. So a quick summary of how we did that: we took our shallow water equations, which you saw earlier, and linearized them about this perturbation beta prime. So eta prime and u prime are the deviations in eta and u given the perturbation beta prime. And then we formulate this duality relation with some adjoint variables and our shallow water constraints. And then integrating this duality relation by parts, we end up with this expression here where the terms highlighted in red go to 0 due to our periodic boundary conditions in space and the initial conditions of our forward system. And then what's left in blue, if we pick the following adjoint system here, so this expression, if we pick it to be such that this is equal to our observations minus our forecast at our measurement points, and we set this term here to 0, and we have final time conditions, then essentially by solving this adjoint system, our duality relation gets reduced to this expression here. And going back to what we said before, this looks like our Gateau derivative equals to the inner product of our perturbation, and then whatever has to be here has to be our gradient. And using this method, we're able to extract the gradient of J with respect to beta, and we can do this analytically, where this is the solution of the velocity of our forward equations, and eta star is the solution of our adjoint equations. So just to summarize the entire process, first, we pick an initial estimate for our bathymetry, which we'll call beta naught. And so in our studies, we always set the initial guess to 0. We solve our shallow water equations from 0 to our final time t to get our velocity and eta, our surface perturbation. Then we solve the adjoint problem for our adjoint variables in backward time, so from capital T to 0. And doing this lets us define our gradient the way we derived it earlier. And then with this expression for our gradient, we can use a gradient descent algorithm to iterate through guesses for the bathymetry beta until we reach some suitable tolerance where the gradient has been effectively reduced to 0. And the bathymetry that gives us this 0 gradient is our optimal control, which minimizes our cost function and hence gives us the minimum error between our measurements and the forecast state of the sea surface. And so in the actual computations, we considered 3 cases for the results. So we looked at 2 cases with a Gaussian initial condition and a Gaussian and a sandbar profile bathymetry. So keep in mind that this is not to scale, it's just showing the different shapes that we used. And then we also considered a case with a periodic initial condition and a Gaussian bathymetry.
Excuse me, so this is the actual bathymetry that you're trying to recover?
Yes, yes. So this is the exact bathymetry, but what we assume in the actual data assimilation that we have no knowledge of this, and we set an initial guess.
Yes, you have some
0.
measurements.
Yeah.
Okay, good.
And so just a quick summary of the results, and I'll show a few plots of some of them in a second. The first thing that we saw that we were actually able to reconstruct the bathymetry with a relative L2 error less than 10% for all the cases where we had a Gaussian initial condition. So we weren't able to reduce our error to lower than 10% for the case where we had a periodic initial condition. Secondly, and this was one of the main significant results, was that we saw that we needed our gradient to be relatively smoother than L2 or even H1 in order to accurately reconstruct the bathymetry and remove small scale noise And which makes sense because if we look at the form of our shallow water equations, the term in which the bathymetry enters the system is a derivative with respect to x, and to require classical solutions, we require smoothness on the derivative of the bathymetry as well as the bathymetry itself. And so we saw having the gradient in H2, which we achieved by finding it at L2 and then using a low pass filter to dampen all frequencies in Fourier space beyond a cutoff point, actually gave us a big reduction in small scale noise in the reconstruction. And I'll show a couple of plots of that to illustrate in a second. Another main result was that for the data assimilation algorithm to converge, we required the surface wave amplitude, so the amplitude of the initial condition, had to be at least 2 orders of magnitude smaller than the amplitude of the bathymetry if the bathymetry amplitude was larger than 10% of the average depth. Realistically, this is not an unfeasible result, considering that usually these, the average depth of the ocean is something like 4 kilometers. So, and tsunami initial conditions are quite small relative to that. So this is something that we see more often in reality. Secondly, we needed a relatively larger number of observation points for convergence. So we compared having, for example, 5 observations and then like 45, and we saw there was a big difference in the quality of the reconstruction. And it improved significantly when we had more observations. And then perhaps one of the most interesting results was that we saw that even if the bathymetry reconstruction was suboptimal, the resulting error in the surface wave was orders of magnitude smaller than the error in the bathymetry. So I will illustrate some of these results. So this is a comparison of the reconstruction of the bathymetry in each case, where the top 3 represent the reconstruction when our gradient is in L2, and the bottom 3 is when our gradient is in H2. And so as we can see, there's a big difference in especially the sandbar profile, where we see a lot of the noise disappears, and especially at the base of the Gaussian, in the Gaussian bathymetry. As we can see in the case where we had a periodic initial condition, that it's not fully resolved in the sense that the height of the reconstruction is not that close to the height of the actual bathymetry. However, we see that we've actually managed to resolve the general shape a lot better than we did when the gradient was in L2. And so in this case, this is just a comparison of when we have points, 5 observation points, which is in black, and 45 observation points in red. And these are all with H2 smoothing, so our gradient in H2, and we can see how much better our results are when we have more observation points. And then finally, here is a plot which illustrates the difference in the error in the bathymetry, which is the black line, and the error in the resulting error in the surface wave given this bathymetry. So the blue line represents the L2 error in the surface wave given the exact bathymetry minus the surface wave given our reconstructed bathymetry. And in each case, we can see that the error in the surface wave is actually often a couple of magnitudes lower than the error in the surface in the bathymetry, which is interesting because then if our main interest is to minimize the blue curve, the error in the surface wave, then does that mean having a relatively suboptimal result for the bathymetry reconstruction? Is that actually good enough? And so that is one of the key impacts of this result, if we can actually substantiate further, which is what we did, where we showed that, and just to summarize, we see that reconstructing the bathymetry with a relative error of about 10% is sufficiently accurate for surface wave modeling. And this can help in tsunami forecast models by allowing us to quantify tolerance levels for the error in our bathymetry reconstruction, such that we can accurately predict the surface wave. And also we can then use our knowledge of observation points necessary for accurate reconstruction to find optimal configurations of the observations that produce this low sensitivity. And so this final point especially motivated the second part of the research, where we wanted to quantify the sensitivity a little more rigorously. So we used second order adjoint analysis, where we basically took the adjoint analysis we used to find our gradient and then applied it again to see if we can use the Hessian of our cost function to analytically derive the sensitivity of the error in the surface wave to perturbations in the observations. So just to summarize a little bit, if G represents the error in the surface wave given the actual bathymetry and then our optimally reconstructed bathymetry, then we want to know how sensitive this is to perturbations in the observations. So perturbations in the observations can come from having a different assimilation time, having a different measurement point, having a different number of observations. And the reason that we pick the sensitivity to the observations is that in a realistic setting, these are the one things that we actually have control over. So in experimental design, or actually having a realistic forecast model, these are the things that we can actually impact. And so what we want to address is, if we have a low error in the reconstructed bathymetry, does this correlate to a lower sensitivity of the surface wave error to the observations? Also, how does changing parameters, so such as the height or amplitude of the initial condition or the exact bathymetry, how does that affect the sensitivity? And also the results that we saw earlier qualitatively, such as this plot over here, can they be verified by this more rigorous analytically derived analysis? So first things first, we have to try and find an expression for dG by dm. And so in this case, I used an analysis by Shutyev et al. From 2018, where they applied this to a general function, and then I applied it to the shallow water data assimilation, where essentially if we consider a response function, so our error function in the surface wave, which is a function of eta, u, and our bathymetry, then if we take a perturbation in our observations, then using the chain rule, we can derive this expression here, where the hatted variables are the resulting perturbations on the optimal system that we found in our data assimilation, which gave us the gradient of J as 0. And then, so essentially what we do is we repeat the process that we did before, where we take the inner product of the optimal system and the expression for grad J with a new set of adjoint variables, which allowed us to find another duality relation, so effectively another Lagrangian expression. And then we find an appropriately chosen adjoint system for the adjoint variables P1 to P5, where essentially by solving that system, we are able to reduce the expression for our sensitivity of our response function to our observations to the adjoint variable P3. And so I won't include a lot of that derivation here, it's quite long, but essentially what we're able to note is that the system that we end up with, the adjoint system, is actually a non-standard problem, which is quite difficult to solve. So it had four state variables with 2 forward time conditions and 2 backward time conditions, final time conditions and initial conditions. However, we were able to recognize that this system was actually equivalent to solving the forced Hessian equation for our cost function J, where the forcing term is defined by this expression here. And so essentially, to be able to solve this non-standard problem and extract P3, we need to have an expression for the Hessian. And so we do this by simply applying the same process that we did before when we found the gradient. So remember, this was our expression for the gradient, where we had the gradient of J given some arbitrary perturbation of our bathymetry, beta prime. So now we consider a second perturbation, beta hat, And then the second order ghetto derivative becomes this expression here. And so again, we truncate it by considering a regular perturbation expansion to linear order, which allows us to reduce this expression for the second order ghetto derivative to this one, where F1 is essentially the linear term coefficient in the Taylor approximation. But what that means is that we are required to find expressions for u given this perturbed second perturbation, and also our adjoint variable eta star given this second perturbation. And so what we do is we linearize about this perturbation, and essentially we find the perturbations in our adjoint and our state variables given the perturbation beta hat. And so actually finding those perturbed systems, the perturbed system for the variation in eta and u is called the tangent model, and the perturbed adjoint system is what we call the second order adjoint. And so then by rewriting this expression F1 in terms of these variables here, we're able to reduce it to this expression over here. And then again, using the Riesz representation theorem, we're able to extract this expression here as the second order derivative of J of B given the perturbation beta hat. So now there's one big difference between what we did for first order extraction for the gradient and this, in that the first order gradient was for any arbitrary perturbation beta prime. In this case, we are only able to extract the Hessian acting on a particular perturbation beta hat. And so the reason I think this is because our gradient was actually an element of our space, and we were able to use the Riesz representation theorem to extract it. However, H is an operator acting on the space. So in this case, we aren't able to fully extract the Hessian. However, we are able to extract the Hessian product, which we are still able to use to solve the equation that we need to. And so based on this analysis, I was able to solve the adjoint non-standard problem that I described here, and able to extract an expression for P3, our adjoint variable, which gave us our sensitivity of our surface wave error given the reconstructed bathymetry to the perturbations in the observations. And so key results we saw in there was that a higher error in the reconstructed bathymetry was associated with a higher sensitivity of the surface wave to observations. However, again, as we saw, have a higher number of observations improved this not only the reconstruction of the bathymetry, but it also gave us a lower sensitivity of the surface wave to the observations. And also we saw that as the bathymetry amplitude increases, so does the sensitivity of the surface wave error to the observations, which, you know, it kind of makes sense. If you have a bigger perturbation of the sea floor, then it's more likely to, the surface wave is more likely to be sensitive to that. However, what we did manage to verify is that once again, the sensitivity of the surface wave to observation was orders of magnitude lower than the bathymetry reconstruction error, which we can see summarized in this table here, where in each case, so for example, even when the error in the bathymetry reconstruction was 10% suboptimal, the sensitivity relative to that was still 5 orders of magnitude lower. So this is important because what this means is that our reconstruction is not so sensitive to small perturbations in our observations, which is good because, you know, often there is noise in the measurements that we take, and it wouldn't be very ideal to have big changes in our forecasts and our results based on small perturbations in the configuration of the observations. So to have low sensitivity is quite encouraging. And so in summary, essentially what the aim of this work was to highlight the feasibility and the limitations of variational data assimilation to recover bathymetry and apply it to effectively forecast tsunami models in the future. And we wish to understand how the error in bathymetry can be mitigated. So things like finding the optimal configurations, how we can maximize the accuracy of the surface wave, and thirdly, how can we attain a priori knowledge of how different parameters within the system, such as the amplitudes of the initial condition or the bathymetry or the different types of bathymetry, can affect the surface wave error. Thank you.